Good afternoon. Good afternoon, and welcome. Welcome to this DTU Ørsted Lecture. Welcome both to those of you who are here in the auditorium today, and also those of you who are following the lecture online. And also a welcome to those who will watch the lecture offline, because everything is being recorded, so it can be seen by many more people after today. My name is Rasmus Larsen, and I'm the DTU Provost. It's my privilege to make the introduction here today. As many of you will know, the DTU Ørsted Lecture series has been in place for many years, and it's a lecture series where we invite top scientists in science engineering to come here to DTU to talk to our students and our staff. Now today is a little special in the sense that today's lecturer himself was a part of starting the Ørsted Lecture tradition, I think almost 25 years ago. Because today we will be welcoming to the stage a DTU alumni, a former DTU professor and a leader of a Basic Science Foundation Center of Excellence. But really he is here today because of the remarkable international career he has had with NASA and with the Jet Propulsion Laboratory in Pasadena in California. So Søren Nørvang Madsen is Chief of Planetary Science at JPL. He's also a technical fellow with JPL. Now JPL is an institution with something like 6,000 employees, and they have about 10 technical fellows. So it's not everybody who's a technical fellow. And today we'll hear Søren talk about the exciting science and all the engineering that lies behind that science for the exploration of space that is done by NASA and done by JPL, done by Søren and his teams and co-workers there. I should also mention that there will be the opportunity to ask questions after Søren has lectured, so you can already now think about good answers to pose. And after we have concluded the questions and answers, there will be a small reception out in front of the auditorium, and I'll hope you'll stay on and discuss what you have heard in the auditorium here with your colleagues, perhaps even with Søren himself. So with that, I would like to invite Søren Nørvang Madsen to the podium to give us a lecture about from DTU to outer space.
Great, thank you, thank you. So for me, this is really coming back to the beginning. I actually had my first technical drawing classes in the rooms right over there back in 1977, etc. It was the main building of bygningsingeniørerne, the construction engineers, and the hallway was filled with buckets because it was raining through the roof. It is much better today. So first of all, my colleagues often by saying, you know, when I was 5 years old, I started looking at the sky and I was so impressed by the stars, and I had to work in space science. For me, it was much more random. First, I wanted to be a doctor. Then I realized how much my hands were shaking, so I realized surgery was not probably a good idea. Then it was pilot. Then I wanted to be having a degree in physics, but all the people who got a degree in physics, they actually ended up having students like me in gymnasiet, high school, and I thought, that's not a good idea, I don't want to do that. So by sort of the method of elimination, I said, well, DTU can't be that bad. So I ended up starting at DTU. I ended up getting 2 degrees in the civil engineer line, electronics and electrophysics. So there was a little bit of physics in it. But after that, then what? There was an institute at the time, the Electromagnetics Institute, and I'll refer to that as EMI afterwards. They just blatantly had the motto that join the EMI and see the world. And I just thought, well, okay, let me just give that a shot. So I actually became a PhD student at EMI at the time. My project was about synthetic aperture radar, and I'll explain a little bit more about what that is later on. But I had barely arrived at EMI before good colleagues, some of them here today, Niels Skov, they basically said to me, we need you to do something else, you know. We have all these contracts with ESA and with the EU, and we have a contract where we actually supposed to map oil spills on the Mediterranean, etc. And Niels, he was the radiometer guy, but there was nobody who was the radar person. So since my PhD thesis actually had radar in the title, Niels said, hey, can't you just start working, operating the radar, etc. And it was great. We were off to Toulon in, in southern France, etc. And we were sitting on a pallet in one of the Air Force C-130s. That was not our rental car, but we thought it was funny to tell everybody that it was our rental car. So the very first time we're about to take off, there's something called a loadmaster on a cargo plane like that. And the loadmaster, he had actually forgotten to secure the pallet we were sitting on. So Niels and I were sitting on that pallet, all of our equipment was on that pallet, etc. And as we start accelerating down the runway, we roll backwards through the cargo bay and actually only get stopped by the aft ramp. And now I backed off too much. So what you see there on the side is actually a waveguide that was going from our equipment to the wall of the aircraft out to the antenna on the side. So this was my first introduction to this is never going to work, because I got sent off to a machine shop on a French Navy base where nobody spoke English. And I had actually had Russian in the gymnasium, so I didn't speak a word of French. So how could that possibly work out? But as Niels is my witness, after a long, long afternoon, we actually managed to get everything done with very nice, competent people who didn't speak English and me who didn't speak French. And it was my first lesson in sometimes stuff seems really impossible, and nonetheless, it works out. So with the same system, and we're now in 1983, we actually flew to Greenland, where we instead were imaging sea ice coming down from the Arctic, etc. Well, first of all, along the way, our captain had his 10,000 flight hour jubilee, so we ended up having a fun time. We also made it past the North Pole. So we actually flew 3 times over the North Pole. And the lower image you're seeing right here is actually me lying on the ramp of a C-130. They did have a harness on me just in case I was dropping out, taking pictures of the North Pole. That was what the North Pole looked like. I think it was the 21st of July, 1983. And by the way, just for good measure, we dropped a box, as you can see, with food and other stuff, just so that in case somebody by accident dropped by the North Pole, they could at least have lunch. So it was a fantastic time because I was much of an academic person, but I had colleagues who said, now you actually need to have a real job, do real things, etc. So with that, shortly after that, actually, perhaps I should wait just a second. There was one more thing, because Gudmansen, he said, we also have all of these ESA studies ongoing. It was all paperwork, but we were designing RF microwave instruments for planetary missions. We had deals with British Aerospace in Britain and Dornier in Germany. So we did these dream things, etc., sent it off to ESA, and with that, first of all, we got a lot of good contract work, but I got introduced to people at ESA when, this is my second year of my PhD study, and by the way, the only thing I didn't do was my PhD study. So because of that, I actually ended up on something that was called the Cassini. Cassini is a big flagship mission, a NASA, ESA joint mission that went to Saturn. This was in the early days where it was being designed, and I ended up on something called the Cassini Instrument Definition Science Team. There were 6 Europeans on that team at the time, and you'll get to it later, but the interesting thing was the lead on the US side, his name was Charles Elachi. And for now, just leave it with, remember the name Charles Elachi. So I started going to JPL. And now we're actually going a couple years later, so I also got Radio Parts Fondens travel stipend. I thought, well, this place, JPL, is really interesting. I should go there. So I ended up spending 3 months at JPL early on in my career. I learned a lot of stuff. JPL was absolutely like a Disneyland. Actually, since I'm in Denmark, we should say a Legoland. But other than that, learning all that technical stuff, that's, by the way, a model of Galileo. I joined the JPL softball team, and I joined the Danish Dynamite soccer team. So I just have to say they're not playing nearly as well over there because I wouldn't have qualified. But on Sundays, I was actually playing for the Danish Dynamite soccer team. And one of the funny things is we were playing the Scottish team, the Exiles. And Rod Stewart was playing for the Scottish team, the Exiles. So I was playing soccer with him on Sundays. But it gets even better, because he had a favorite pub, and after the games, if he was there was lots of Sundays where he was not there, but if he was there, we'd all go to his favorite pub called The Bangers, and he always picked up the tab, so beer was free. So I was completely enamored by JPL, you know. I really like this place. During day hours, I actually learned things that I didn't understand before, and when I'm not working, I had a lot of fun. So it was all good times. So back in Denmark, and again, I'm going too fast here. One more thing, because again, it was not much about the PhD. At the same time, you saw the sensor package before. Niels had his radiometers. I was responsible for what was actually a TERMA, what was called side-looking radar. It's not great resolution with a side-looking radar. So I started dreaming about, we should build what's called a synthetic aperture radar in Denmark. And synthetic, we all know, that's fake. So the basic idea, which could be 2 lectures in and of itself, but the basic idea is that to get high resolution, you need an aperture that's big, measured in wavelength. That's fairly easy if it's optical, where your wavelength is half a micrometer. But if your wavelength is many centimeters, now you need apertures that are hundreds of meters of long, if not kilometers. So what was happening at the time was that more and more people got into, well, this synthetic aperture radar, you can fly an aircraft through a path, etc. And in computers, you collect all the data, and then you fake it. You fake it by combining all these data signals, so it looks as if you have a much, much longer aperture, hundreds of meters. So this gets to, I have a few lessons learned that worked for Søren along the way. I started talking about it, but it was all these vaporware dreams, etc. And one of my former colleagues, also Erik Nielsen, he said at some point, you know, I actually heard about a private institution, Thomas B. Tries Foundation. They would like to spend a lot of money on one thing instead of a lot of small projects, etc. So I said, I have the right idea, etc. And so I wrote a proposal for a Danish synthetic aperture radar at that time. And now when I'm hearing about how much DTU gets in terms of money from Novo Nordisk and other places, this pales completely. But actually, in 1985, I ended up getting $10 million from the Thomas B. Tries Foundation. And at that time, it was just a windfall. It was, whoa, a lot of money. I see we have Christian Stubkær here. He will remember that. 10 million bucks on one check. I like it. So we actually started building this synthetic aperture radar. And this is some of the people from that time. One of the pleasures I've had is to work with some really, really great teams through the years, and this was one of the best ever. People worked like crazy, and they partied like crazy. To make this possible, one thing was you need a team, and you need a big check, $10 million. But we had also benefited from the fact, and it was more than anything, Niels, who had developed a relationship with the Danish Air Force. So when we said, we need an airplane, but even with $10 million, we can't buy an airplane. We need support here. So they had some Gulfstreams. Well, that didn't really work because we also had we needed some places to put our antennas and other things. What you're actually seeing up here, they gave us an expended fuel tank from a Draken fighter planes. That was what Denmark actually had before 8 F-16s, etc. So they gave us a fuel tank, and we just went to work. We just started calls in it, etc. We found some people over on the mechanical engineering quadrant who could help us, etc. And we went off to work. And here's another picture. It was pretty crazy what we were doing. We took the pod, by the way, with an antenna, put it up in the radio anechoic chamber, etc. You see the racks over there. Upper left-hand corner, that's where you can see what it looked like early on. Later on, we made more additions, so there's a little bit wrong with the chronology here. But if you look very carefully, the resolution isn't great. We put all kinds of streamers on it, then we would take off with that, and then the Air Force would actually fly with an F-16 next to us and take pictures. So with all the streamers and all the pictures, we could actually see that the airflow was okay, and then after talking to a few people, they said, qualified, air qualified. And it was just great times with lots of action. So that led to, in 1989, we did our first test flight. And I'm sure all of you now look in awe and say, that looks great. This is actually what the imagery looks like before you send it into the computer. This was the raw radar data. I know you've seen this already, but this is Copenhagen. So the airplane is flying somewhere over Roskilde. But now, as you go on, this was the first step in the processing, something called range compression. And magically, this is the same data that you saw before. This is the trick of synthetic aperture radar, that you take all that garbage data you had in the first place, and you do enough processing on it. Then suddenly, even our first flight, we actually got this data set, and we were just all on Sky 9 thinking this was fantastic. And Jørgen, you don't have to say to everybody that this was actually not full resolution. It should have been 1.5 meter resolution. But on the very first flight, we ended up with 6 meter resolution. So that's what you're seeing here. But we were absolutely, whoa, it's all working. At the same time, I mentioned before, I was now going to the US all the time. And the JPL people, they especially wanted my opinion on their radar for the Cassini mission. And I looked at the design and I said, this is never going to work. And they looked at this kit from Denmark and they said, oh, absolutely, it's going to work. All of our experts have looked at it. It's definitely going to work. So I came back to the lab at EMI and I said, they're not listening to me. I'm telling them it's not going to work. And I remember it was Niels and it was Jesper Hansen, who was our antenna professor at that time. They listened to me and they said, you might be right, perhaps it's not going to work. So talk to a company called Tigra that was actually a spin-off from EMI, and they had become world famous for their antenna analysis. So I joined these Tigra people and I said, hey, I don't think this is going to work, and this is why, but they don't believe me, etc. So TICA, they wrote a report. It was only 12 pages or something like that. So on my next trip to JPL, I showed up with this TICRA thing. Charles Alati didn't know what TICRA was, but the JPL antenna people, they said, oh, TICRA. Oh, let's read it. And then they started looking at each other, and they said, it's not going to work. And after a day or so where they had mulled it all over, they said, it's not going to work. So as a consequence of that, two things happened. One was that they actually changed the radar design, specifically the antenna design completely. And 2 months after that, I got a job offer from JPL. So I'm oftentimes saying, most people, they get hired because they do positive things. I've invented a new things. I've done this or that. I got hired because I said it's not going to work. So anyway, things were going well in Denmark, and at that time, I actually ended up accepting that job. And on the 2nd of January 1990, I started working at JPL. And just in case you don't know what JPL is, it's a place that actually was started by students, like I believe there's a lot of you who are students, from Caltech. They had started a fire down on campus that was really not good during their testing. So basically, they were told by Caltech leadership that this is not going to work out. So you have to move up north of there. There was a gravel pit, which is literally where JPL is located today. It was a gravel pit where they started doing all their rocket experiments. And they actually got so good at it that that they built missiles for the US Army in the 1940s. So the first US missiles were either made at JPL or at the Goddard Space Flight Center on the East Coast. And JPL actually built and flew the very first US Earth orbiter called Explorer 1. And the people you see there on the left-hand side with their hands up, that's JPL's director, Pickering. And the next one is Van Allen, and the last one is actually Werner von Braun. And the interesting thing was Explorer 1 found the radiation belts called the Van Allen belts at those times. JPL today is something completely different, and I could also spend hours on that. Mostly what we do is planetary science, and I'm sure you've heard about the Mars program, rovers on Mars, etc. But also all the other planets, astrophysics, Earth science, but not here. We actually also operate something called the Deep Space Network. We have antennas in California, we have antennas in Spain, we have antennas in Australia. That means that no matter where we are and how the Earth is rotated, we can talk to all our spacecraft at all times. But more than half of our activities is actually planetary science, including Mars exploration. So the very first thing I got to work on when I came to JPL was a mission to Venus. Venus is interesting because if you look at Venus optically, it has a very, very dense atmosphere and you can't see something. So it is the perfect application for radar because of the very long wavelength. Radar can actually penetrate down to the surface of Venus. So Magellan was also my introduction to the drama of space missions. When we're all sitting, nowadays it's probably at YouTube or something like that, and we're saying, cool, these people really have their acts together. Well, on Magellan, basically, what happened was that 6 days after orbit insertion, the radar got turned on for the first time. And we linked down data to the Deep Space Network, and we lost communication with the satellite. So as far as we knew, it was gone. So on the 16th of August, that was now we're 1990, I actually get a phone call, landlines before cell phones, at 11 o'clock at night, and they're saying, Søren, you need to come to JPL because we have lost a satellite, we have 1.5 hours worth of data, and the processing system doesn't work. So as John knows very well, I'm a super paranoid person. So the processing system was 4 racks of electronics, etc. And I said, that's never going to work. So I had actually built my own little software processor back in the days where computers were really, really slow. But I actually made it to work, and before midnight, I had processed the first data from Magellan. So that also raised my star at JPL a little bit. Oh, okay, all the official stuff that they had worked on for 4 years, that didn't work, etc. It was my luck, because actually 6 hours later, their system started to work, but I had a window of opportunity that was 6 hours. The other thing that I got to work on was shuttle radars. There were actually a number of them at JPL. The one I got to work on was called SIR-C, and I'm sure everybody knows what that means, but it's SIR, shuttle, imaging, radar. C just means number 3. The others were called A, B, and C. And at that time at JPL, there was something really interesting in that synthetic aperture processing actually requires really a lot of computations. Those days, computers were insanely slow. So most of the processing was actually done optically with holograms and whatnot, super complicated. At this time, we just started doing imagery on computers, and contrary to optical data as technology is implemented today, each and every image point is actually not just an amplitude, it's an amplitude and a phase. And there was a guy at JPL at the time, Richard, I was never called anything other than Dick Goldstein. He started experimenting with the digital data and said, if you actually lay 2 sets of data on top of each other, either acquired you image from one location and a slightly different location, or same location but at different times, you could actually measure minuscule, truly small changes and displacements. If your antennas are positioned spatially off each other, you can use that to do triangulations, you can do topographic maps, etc. If you're offset in time, you can use this to measure very slow velocities, and we'll talk a little bit more about that. So I got to work on space shuttle. How cool is that when you're used to a Gulfstream G3? So, but at that time, I then got offered actually from Denmark something called et forskningsprofessorat, a research professorship, which was 5 years. You didn't have to teach, and you actually got a research grant at that time. It was $500,000 kroner or something like that. And I thought, God, that's really, with my vanity, I would like to be a forskningsprofessor, etc. But again, remember Charles Alachi. Charles Alachi at that time had actually made his way up to what was called an assistant lab director. He said, no, JPL has a lot of good stuff going on. And I actually had to admit I had a good time, a fun time. So Charles said, you're young, you can do both. So for 3.5 years, I was actually employed 20 hours a week by DTU and 20 hours a week by JPL. So just want to say to everybody who feels sorry for themselves because they have a long commute from Solrød or Køge or Espergærde or whatever, for 3.5 years, this was my commute. So from about, I think it was May of 1993 to the end of, actually to the end of 95, and 93, 96, I was doing this back and forth and back and forth. So just for the fun of it, I recently, for a background check, they have to make sure that you are actually still reliable in the NASA system. I had to list all of my international trips. And good thing that you actually get listings of your frequent flyer miles. So about 2 or 3 years ago, I was at 220-something trips across the Atlantic. So I'm still waiting for this letter from Scandinavian Airlines. Thank you for your business. So again, just listing. So I already talked about the first part, 90 to 93, at JPL and DTU, 93 to 96. At DTU, I was actually here full-time for 3 years, 97 to 99, and full-time at JPL since then. So, back in Denmark, while I had been gallivanting in JPL and just having a good time, I was no longer playing soccer with Rod Stewart. My good colleagues here at EMI, they had improved on the original concept of this black and white radar, etc. They were developing something called polarimetry and other things, etc. And it was going really well. So when I came back, the deal was, what now? And once again, somebody was saying, there's something new in Denmark called Danmarks Grundforskningsfond. I think the Danish National Research Foundation. And once again, it was, well, why not write a proposal? The worst thing that can happen, that is that you waste a few weeks, etc. So I actually, with the help of a lot of good colleagues and friends, wrote a proposal to Danmarks Grundforskningsfond, and that ended up becoming the Danish Center for Remote Sensing. And we have a number of employees actually here from that time. And that led to many things. First of all, I should say, even before the EMI environment was super active, it's not as if I started anything. Preben Gudmandsen's group that I was part of, they actually had been looking at satellite imagery for 10, 15 years at that time, if not longer. Henning Skriver, who's now the director of DTU Space, he was looking at Landsat imagery, etc., doing analysis, trying to figure out what crops there were. There were other people, Leif Toldal Petersen, who was actually imaging sea ice and seeing way before everybody else that the sea ice is shrinking. This is not good. It took a long time before people really realized that. But with all the money we had gotten from Grundforskningsfonden, we were also able to now introduce my favorite topic, which was more radar stuff. And this is one of the examples we did by doing interferometry, as I mentioned before, at that time with a new European satellite called ERS-1, Earth Resources Satellite number 1. We could combine these phase images from multiple tracks, and from that we were able to, way back in those days, to what you're seeing on the right-hand side, the lines are actually height contours, and the small arrows were measuring velocities of glaciers. And if you look at what happens today, 30 years later, and we were, by the way, not the only people doing that. There were people in Germany and Italy and France doing the same thing, also the US. When you're reading about global warming and how the ice is disappearing, etc., this is one of several elements that is used widely today. But those days, it was really cutting edge. Is it going to work, etc.? Fun stuff. So, and now I just need to make sure, because I know I have too much stuff. Number one, by the way, this was the same time where we added also this cross-track interferometry. You've already seen the two images, the two antennas on the side of the Gulfstream G3, which actually allowed us to be able to fly a trajectory and then instantaneously make a height map, which was very cool. We did another thing that was really nice. I had sort of stolen the idea from some other people who did it with a laser, but that was, we got our radar to actually fly the aircraft. There was a little bit of reluctance in the Air Force in the beginning. Okay, you want to fly the airplane. No, it's not even you who wants to fly the airplane. It's actually, you're saying your radar should fly the airplane. But we actually sold the idea. And we had a system where the radar would literally fly the airplane along a given trajectory. And what we used it for was that sometimes we wanted to be able to fly exactly the same place through space based on a GPS coordinate. That was a wonderful invention at that time. Or sometimes we wanted to fly the same trajectory with 20 meters in between or something like that. We did a lot of very nice research. Unfortunately, we never really managed to use that productively. But my colleagues back at JPL, they got so envious. They said, "Whoa, that's a cool idea. We want to do that." So JPL actually copied our idea, just did it way, way better. So JPL today, we have 2 Gulfstreams. We are calling them UAVs because originally it was supposed to be on an unmanned vehicle. It isn't. So this system at JPL that was really modeled after the DTU system at the time, we can actually repeat a trajectory in space to an accuracy of 1 meter. And it's actually with wind and other things, it's not easy at all. But so we did something first in Denmark that those damn people at JPL thought was a good idea, and they decided to do the same thing, just better. Let's see. Another thing happened at that time. So first of all, I actually had a kid, a son, and then the flying back and forth every 6 weeks, etc., that ended up being impractical. So this was a time where I actually ended up working here in Denmark full-time for 3 years. And when I was at JPL, I always went to something called Caltech's Watson Lectures. Every time I was in town, I would go to the Watson Lectures. So when I came back to DTU, I said, we should have something like the Watson Lectures. And that's actually what we have today. That became the Ørsted Lectures. The ambition level, I said, we need Nobel laureates. I would not have qualified. I would not have invited me. Let's just be clear. But if you look at it, so 2 more people really deserve initial credits, because in Denmark, if you think about a Nobel Prize, what do you think? Bohr. So the first person I actually contacted was Jakob Bohr, who was also a professor out here. And Jakob said, we need Jørgen Stavnstrup, and I know he's not here today, but Jørgen Stavnstrup was also part of the original 3 Musketeers. And here's just a list. I don't want to go through it, but I can give my brother, who's sitting right there, credit for finding the first lecturer, Ivar Giver, because my brother came back and he said, I've just been at Cornell, and I was having lunch with this Nobel laureate from Norway. He was really an interesting person. I said, I'm going to invite him. So this is actually where the Ørsted Lectures, and you can see, by the way, now Charles Alachi. I said, Charles, can you come here, do us a favor? Dr. Leroy Hood, who's, by the way, on the next one, he was actually my significant other, Cecilia's PhD advisor at Caltech, and Leroy Hood has won everything except for the Nobel Prize. And he also said, sure, I'll come. And finally, I just want to say, look at the room. This is the room you're sitting in here. So except that they have upholstered the seats, etc., and I think actually the woodwork is new, etc., the room looked exactly the same 25 years ago. Anyway, I'm just so glad that it's still ongoing. And 25 years later, everybody thinks it's a good idea. Very cool. Thank you very much. All right. 2000, I fly back to JPL, and I'll go a little fast because it's radar, radar, and radar. We actually took what was the Cersei radar you saw before. That was in the bay of the shuttle. And then instead of our short baseline on our G3, we actually had a 60-meter long boom, put another outboard antenna, receive antenna on that. And with this system, it was called the Shuttle Topographic Radar Mission, SRTM. We actually made the first global homogeneous topographic map. Before that, everything had been stitched together of national maps, and they were done at different resolutions and everything. And it was about a plus minus 60 degrees, has to do with the orbit and the fact we looked to one side, so it was actually a little more on the northern side than on the southern side. So that was one of the things going on. The other thing, which was a little bit closing the loop, Cassini, that had been my original connection with JPL, had been built, had been launched, had made its way to Saturn. It actually orbited Saturn, but was doing close flybys of Titan work, and I actually got to work on the radar images. And this is us cheating a little bit, but what you're seeing here is actually radar images of Titan. And Titan is another one of these systems in the solar system we're very interested in because it's called an ocean world. There are actually oceans, there's wind and other things, but it's hydrocarbons because otherwise it would have been freezing up there, so probably don't drink the water. But anyway, that was great. By the way, as I left DTU, one of the reasons was that I thought, as the head of the Danish Center for Remote Sensing, I was spending way too much time in meetings and this and that, and I didn't get to do much technical stuff. So I had fun for about a year, and then it didn't really work out for me because I actually ended up being the head of radar science at the JPL, which was 100 people. So I also ended up doing too little technical work there. So, because I know I have limited time, I'm actually fast forwarding 5 years. So after 5 years of being the manager of radar science and engineering at JPL, one day the assistant director came to me and he said, we have this Mars program, and right now the Mars program is really important for us. And we have 2 instruments, and they are broken. It's really, they're over budget, they're behind, and everything. And I said, which 2 instruments? Well, one of them was called Kemen, and it was an X-ray instrument. The other one was TLS, which is part of what's called the SAM suite. SAM was really 3 things. It was a mass spectrometer, it was a chromatograph, and it was this laser, tunable laser system. And hey, I'm from EMU, Electromagnetics Institute, and whether it's X-rays, or it's laser wavelength, or it's radars, it's all electromagnetic waves. So the fact that it's from X-rays to radar, that's 8-9 orders of magnitude difference. How hard can that be? I got through my experience in France in the machine shop, so I said, yeah, sure, sign me up. So I joined what at the JPL was called the Mars Mafia, because they were very sort of, okay, we are the ones going to Mars, etc. And by the way, as a small addendum to that, about 6 months after that, I ended up also managing the landing radar, because the landing radar got in trouble. And then they actually said, well, Søren, you should do that because you actually know how to spell radar backwards. And I said, sure. And it was a little bit like my first team, by the way, at EMI, people who were working insanely hard and just fun to be around, etc., and were good at just getting the job done. So at this time, I also got my introduction to JPL as an outreach organization, because I don't know whether you have been following some of the things happening at JPL, otherwise I'll force you through a little bit of it here. But when we spend billions of dollars of taxpayer money, we actually make a point of bringing people along and just see what we're doing, try to get some enthusiasm, etc. So, and I just want to say, from my point of view, one of the things that I found really impressive, as we're landing on Mars, we will actually phase and make sure that our orbiters are in the right place at the right time. So we had one orbiter called the Mars Reconnaissance Orbiter that was anyway going to fly over because we needed it for telemetry. So as you're coming down on the parachute first, etc., then we're actually not linking data back to Earth, we're linking data back to a satellite. That satellite immediately sends it back to Earth with 0 delay there at that point, and it was MRO. So somebody said MRO actually has a really high resolution imager. It's called high-rise. And the aperture is literally 0.5 meter. So it is super resolution. We actually use it to make maps of Mars so we can see where it's safe to land, etc. The resolution at a 350 kilometer distance is 30 centimeters. So, but somebody said, why are we not, since we're flying by anyway, why are we not steering high-rise towards where the spacecraft is coming down? So this impressed me, I just want to say. So we're back in 2012. This is a satellite flying past full speed. And what you're seeing right there, that's the Curiosity rover on its parachute. The Curiosity rover with back shell and all is hanging below it. And if you actually do the math of how accurate the timing has to be. You need to take, it's one of those things where have your camera ready because you have like 20 milliseconds, etc., because you are flying by at 4 kilometers a second, etc., and at the same time the parachute made it down, and we had to predict about where we were going to be. The field of view for high rise at that distance is only like 4 by 4 kilometers, etc., so you better aim right. So perhaps you're not impressed, but I was. So, by the way, a few orbits later, we flew by and then we looked at all the debris, etc. You can see where the rover landed. Sky crane, you'll see what the sky crane is, but that's basically what we lifted down on, was over on the side with all its propulsion. The heat shield was there, the back shell, which is the back side of where the rover is packed up, and the parachute was there. This was also. So this is one of the things today at JPL. We'd like to do great things, something that really helps science, etc. But there's also a culture of every time we do something exciting, let's get it out there. And by the way, if we screwed it up, every time we think we have 95% of success, so 1 out of 20, we would actually statistically expect it to not work. But you're with us, and there's no 4-second delay so that this is not going well. Let's cut the feed off and not show the world. The world is literally with us. So, now I need to go really fast, I can see. After that, I spent some years as the chief engineer for the Mars program. And I'll go really quickly. That was just looking at the architecture. We had orbiters up there. We had the Curiosity rover. At that time, Perseverance was something that was planned, etc. And once again, my life ended up in a lot of meetings. I did have one fun thing. I was actually leading a Tiger team when Spirit got stuck up on Mars, etc. But otherwise, fast forward. So my next job was as the payload manager on Mars 2020, what today is called the Perseverance rover. Amongst friends, Percy. So what is a payload manager? Payload manager is a person who's responsible for getting all the science instruments delivered. And there's actually a DTU angle here. If you look at the Pixel instrument, that's an X-ray spectrometer. John Leif Jørgensen and his group, they delivered not only the camera, but a very advanced lighting system that both had something called structured lighting, so we knew exactly how far we were away. And John likes to talk about his multispectral stuff also. Niels Bohr's Institute, they were also part of this. They've actually specialized in making small magnetic systems because it's very dusty on Mars, but the dust is magnetic dust. So you'll actually see that there's rims of dust around the calibration target, but the calibration targets are very clean. And that was all the Niels Bohr Institute at the University of Copenhagen. So, by the way, I just wanted to, in 15 seconds, show the teams had grown a little bigger. When we were at the peak for 2 years, we actually had 800 full-time equivalent people working on Mars 2020. And when I say full-time equivalent, that means when there are 2 of us who are working half-time, we only count as 1 person. So I think in this photo here, there's about 1,000 people, give or take or so. But it also taught me something about you manage small teams in one way, you manage bigger teams in different ways, etc. But it was great times. So with that, the next level of let's bring the public with us. So my boss, his name was Matt Wallace, his daughter was a fantastic elite gymnast. She's one of these people who just do flips all here and somersaults and whatnot. And Matt gave her a camera to wear on her chest while she was doing all of that. And he was looking at and showing the rest of us, look at all of this stuff. Now the ceiling is up there. Now the ceiling is down there. We were all a little bit dizzy. But he said, we should do the same thing for our next mission. So literally that story led to that for the Perseverance landing, we had put cameras on the descent stage, we had put cameras on the rover on the top side looking up, we had cameras on the bottom of the rover looking down, etc. So 3 minutes here. So straighten up and fly right. That's actually, we literally fly
in preparation for parachute
lander
deploy
on the heat
and to
shield.
roll over to give the radar a better look at the ground.
The radar.
Indicate chute deploy.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
So by the way, if you were wondering, what was that weird pattern all about?
Heat shield set.
We're not allowed to write JPL on our missions. We have to write NASA.
This allows
so the
both
pattern
the radar and the camera
was
to
actually
get their
a Morse
first look
code
at the
that
surface.
said,
Current
"They're
velocity is
mighty
145
things." That's
meters per
JPL's
second at an
motto.
altitude of
On the
about
previous one, on
10
Curiosity, we had
9.5
actually made
kilometers
holes
above
in
the
the wheel,
surface.
so every time we were doing another revolution, we in Morse code said JPL, 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 JPL. So now we're coming down here and actually doing something called terrain relative navigation. So other than the radar knowing how far we're away, how fast we're moving, we had a map
Nav filter
on
converge. Velocity solution.
we had a map on board of safe areas and
Altitude
non-safe areas.
7.4 kilometers.
Now
So
has
at
radar lock on the ground.
nearly
Current
here.
velocity is about 100 meters per second,
At
6.6
4.2 kilometers above the
surface.
surface, we actually picked exactly where we would land. So now it's actually doing a divert so that it steers to exactly where we had we wanted to land.
Relative navigation and subsequently the timing of the landing
relative
engine. Our
navigation.
current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
Oh, so this is where we picked the landing point actually.
LVS valid.
We have confirmation
So-
that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
And down here you can see
We
where we are.
have
We have
timing of the
rejected
landing
heat shield
engine.
at this point.
Back shell set.
Current velocity is 83 meters per
Backshell
second at about
separation, so now the
2.6
lander,
kilometers from the
the
surface
sky
of Mars.
crane and the rover,
We
they're
have
on their
confirmation
own.
that the backshell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about 1 kilometer off the surface of Mars.
75 meters.
Here in safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are
Now
conducting
we're
the
close.
sky crane, about to conduct the sky crane maneuver.
That's where we lower
Sky
the
crane maneuver
rover
has started,
on the bridles. This is the sky crane on top.
about 20 meters off the surface.
Wheels unfold. Cut the wires, the bridles.
We're getting signals from MRO. Tango Delta.
Tango
Touchdown
Delta,
confirmed.
that's touchdown.
Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
So very cool, and again, tradition of sharing with the world. By the way, if you're following Perseverance, it's been immensely successful. It's been driving over 30 kilometers, actually close to 32 kilometers. But there was a little bit of another thing. That's the yellow track you see. The blue track, what is that? Well, we actually brought a helicopter along. A helicopter we didn't want because we didn't have space for it and we didn't have money for it. But in the end, the helicopter made it. And the helicopter has been spectacularly successful. I didn't have time for another video, but we actually managed to take video with the cameras we have on the rover of the helicopter, video from something called Mastcam-C. We had a microphone on something called Supercam, so we could actually, you can find on the web videos of the helicopter flying with the sound and everything. I greatly encourage you to go and look at it. It was supposed to do 5 flights and then we would have declared victory. It actually did 72 flights. It was basically built with cheap commercial parts, but a fantastic success. So now we're planning on doing science, helicopters, and things like that. So, what's next? Perseverance has assembled about 25 samples plus 3 witness samples at this point. We want to get up and collect those samples and bring them back. We were on our way to do that, and it ended up to be explosively expensive. So right now we're in a replan mode, but nonetheless it won't change too much. The basic ingredients will be, we're going to land something we're calling the sample return lander. That's what you're seeing on the lower right-hand side. We're going to have a rocket in it that we're actually going to eject out. You don't want to put it on its upright, because then you actually have so much debris coming up. So we're actually throwing it sideways up, and then we have a generous 1/10 of a second for it to ignite. Otherwise, it's going to fail. And then it's going to take all the samples up. I failed to mention that Perseverance will actually go and load all of those samples in the front of the rocket, where there's a ball that's about a baseball size, etc. And then we're going to fly it up where there's a European contribution called the Earth Return Orbiter, a really huge satellite that's going to take the samples back to Earth. There's a little bit of debate whether we're actually going to put them in orbit about the moon or flying them straight down to Earth, but that's the big thing. So this is truly getting to the end of it. The last couple of years, I have spent a lot of my time on something called Europa Clipper, and it's very fitting. It's going to orbit Jupiter, but what we really want to study is the moon called Europa. Current estimates are that Europa has, and by the way, I should say, Europa is about the size of our moon. Current estimates are that Europa has 3 times as much water as Earth has. Now, but it's cold out there, so therefore, if you're looking up there, way on the edge, you see the blue stuff, that's sort of an artist's concept of the water. But obviously, the top of that is frozen solidly. So one out of many instruments that I just want to talk about in the last 2-3 minutes I have here, that is a radar, a sounding radar. And you see the long stick antennas here. And the interesting thing was, as I was working on this, there was actually a New York Times journalist who said, "What's your accent?" And I said, "I'm Danish." "Oh, that's interesting," he said, "because I'm writing about Europa Clipper and the radar sounding. And all that radar sounding, that started back at the Technical University of Denmark." And it actually did. So that's another day, but it was actually people like Preben Gudmandsen, again Niels, and Erik Lins Christensen, etc. They started out building these sounders and measured thicknesses of ice in Greenland, Antarctica, etc. Well, now we're going to do that on Europa, etc. Very cool. So, well done, DTU. Next one is just some pictures so you can get an idea how big this spacecraft is. Look at the solar panels here. They're actually deployed. They're over 30 meters tip to tip, etc. So, fast forward to May of this year. I'm sitting in my office Sunday, the 5th of May. Well, I'm assuming you're also sitting in your office on Sundays. So the phone rings, and it's my boss, Matt Wallace, again. He said, "Søren, we need you to take one for the team. We have a problem." Problem was that we had discovered that some radiation-hardened MOSFETs were not as red-hot as they should be. As John knows more than anybody, Jupiter, especially when you get really close to Jupiter, is really brutal in terms of radiation. So I actually got tagged to make an assessment, and now it's official. We couldn't talk about it originally, but some journalist from the New York Times actually got wind of this, and therefore I can't talk about it. We found out that we have 1,500 transistors that were not as radiation hot as they should have been. So from the 5th of May to the 27th of August, with the exception of one day, every single day of the week, I'd be working on, can we launch or can we not launch? Because if we can't launch, we actually need to bring the spacecraft back from the Cape, take it apart, etc. And the lowest estimates of the cost of doing that was $500 million, not kroner. So going really fast, end of August, we actually got to, yeah, this is good. I had to just get my name in there one way or the other. I wish it had been 34-year-old Søren but it was 34-year veteran. Okay, damn. But anyway, long and short of it, by the end, it ended up being if we change the way we use the electronics, it's going to work anyway. So go, go, go. Lots of drama, lots of hard work, etc. And I actually, exactly 10 days ago, except for 2 hours, it's 2 hours later in the day, we actually launched a Clipper. And I was there, and it was a great day. Big rocket. It was one of SpaceX's Falcon Heavies, and on this case, we needed so much acceleration that there was no landing the rockets have been on Earth. We used every drop of fuel there was. So, getting to my final chart. So here's the trick for all of you. Number one, you start at DTU. Got it? You work hard. Make sure you have great mentors, people who can teach you things, who can get you out in the corners, etc. Don't be afraid of taking chances. If I give myself credit for one thing, that is I have been crazy and actually tried things I probably should have said no to, but somehow it ended up, sure, why not? I highly recommend that you're lucky. It has worked out really well for me, definitely. I would say keep learning lifelong, otherwise you want to retire early. So the one thing I wanted to put in here, that was actually my international student identity card, because I still consider myself a student today. It won't be boring, and it's much easier to deal with work-life balance if work is actually a very large and positive part of your life. It's easier to get the math to add up. So that's really all. Thank you.
Thank you, Søren, for a very enthusiastic and deep introduction to how a life in technology and science can work out. It's highly appreciated. It was fun to see some of the old stuff. We have been students together out here at DTU many years ago, started the same year. So it's been funny to see how your career has been rocketed off elsewhere. We have a few minutes for questions here, if somebody has something to ask about. I know there are many topics, but please don't be shy.
You mentioned there was a chance that you took, but you should have said no to that. What was that?
But it was just sometimes it was really busy. I can say when I was managing 3 instruments on MSL, by the way, if I had had more time, I would have talked about positive and negative stress, etc. Probably sometimes I should have been the more sane person and say I'm already working 75 hours a week, so I should probably keep it to that. But I think when I'm looking back at it, and I was trying to put this talk together, it was just, yeah, that too, etc. And some of the things, if I had thought more about it, I probably should have said, that's never going to work. But that's the lucky part, that somehow everything actually ended up well. And in no small part, I know I'm repetitive, in no small part because I just have always been so fortunate that I've had really good colleagues. And good teams, that's where people really help each other. If you're coming up short, then somebody else will actually make up for it, etc. So again, if I had been more sane, perhaps I had said no, because that's never going to work. But it ended up working because of good colleagues, good helpers, and everything.
Somebody here? Yes. I think you were. Who was first?
We'll just take
whichever. Oh, you can take the one.
Thank you so much for the presentation. I also wanted to hear, what is the biggest personal challenge or opportunity for personal development through your career?
Oh, so for personal development, then I actually have to, because if you had stopped at challenge, it would have been a different answer. But if you said for personal development, it actually, that's the reason I had all the early stuff there. I have to say what has worked really well for me was that I was forced into so many different things. Academics was fairly easy for me, but all of the experiments, etc., you gotta actually get systems to work, writing reports for ESA, writing proposals, etc. So I think for me, personal development was more than anything that I did so many different things. John and I were talking about it earlier today, being poly, whatever, but many-sided. And I have to say today, where I'm the chief engineer, it's not so that I'm the chief engineer for electronics or electromagnetics. Next week, I might have a mechanical problem. So what really, really has helped me was just the diversity of things that I got forced into, but somehow anyway said yes every time. But I just did so many crazy things. And later on in my career, that has just really, really helped me.
Yeah, so thanks for the presentation, and just maybe piggybacking on that previous question, but looking forward, and very specifically for Reason, what do you think is going to be the most challenging aspect of Europa for Reason?
For Reason, good question. Number one, I do think we now have a fairly good handle on electrostatics, which is the reason receivers are so sensitive that we actually have to deal with something called IESD, internal ESD. When you're flying in the Europa environment, just because of all the charged particles, you literally have sparks flying all the time. So for Reason, that was the radar called, and it stands for something like Radar for Europa, REA, assessment, sounding and ocean near and surface, yes. Every time we hear one of those pops, we actually pick up on them. And there has been a lot of concerns about that. So I think that is going to be an interesting thing, whether we have problem. Our assessment is that we're being okay. But just to give people, and it sounds as if you're on board with this, we expect like close to 1,000 of these pops per second as we're flying by Europa. So that's going to be interesting. It is going to be interesting what happens when you get further down in the layers because of the saltiness and other things. Clearly one of the things DTU discovered many years ago, that the salinity of the ice, the temperature of the ice matters, and we don't know what we're going to see because nobody has done it before Reason. So, but very cool.
Could you say something about your risk analysis of using those microchips in radiation environment?
What I can say is we had a gigantic test program. So I was actually, as I was running that, there was no bars hold. There was a blank check. You can spend as much money as you will. We spent $10 million in 4 months. We were doing testing at JPL. We were doing testing at the Applied Physics Lab on the East Coast. We were doing testing at Goddard. So number one was we actually had to characterize 60 different parts types. I said there was 1,500, but there was 60 different ones, and we used them in different ways. So what we ended up doing is not percentages. We actually ended up determining that with certain mitigations, as I said, that we were changing when things are turned on and how hot they are and other things, everything would meet typical JPL margin standards. So I can't put a percentage on it, but it was sufficient that we would actually be able to, we didn't cut any corners in probability space. But by the way, there's some of this that we're still trying to figure out what we can share and what we cannot share because it's a very sensitive area. There are other areas where high radiation stuff is of importance.
Let me ask you a more, less constrained question. When do you think people will walk on Mars?
I'm not planning on retiring anytime soon, but I will have retired by that time. I can guarantee you that. So I actually think that most of the current estimates are just not even close. So if we cannot get samples back from Mars, how are we going to get people back from Mars. And right now, we're looking at picking those samples up probably in 2031, having them back on Earth, depending on whether we get to have to drop them off on the moon or circle the moon first. 2033 at the earliest. So people, 2045, but I would not bet something that I could not afford to lose. So I'll bet a beer because I can afford to lose a beer. But I think it's anybody's guess.
Thank you. I think we need to call it a close today because time is running and there will be a reception outside. Do you say something about this? Or?
Yeah.
Okay.
Then I'll just grab that. Thank you, John, for leading the Q&A session. And what remains for me is just to thank you again, Søren. And there's a small token of our appreciation here, a small gift in the bag that we'll hope you'll appreciate and take back with you. And then I'll invite everybody to come outside for a drink and a sandwich and further discussions. Thank you very much.
Thank you.